Good morning, ladies and gentlemen, and welcome back on stage for day 2 of our very first Bitkom Quantum Summit in 2021. Yesterday, we had some great insights, we had panel discussions, we had Q&As, we even had a fireside chat. And today, we want to continue our journey to learn more about why and how quantum technologies are a real game changer in today's world. For those of you who haven't had a chance to join us yesterday, just some quick informational insights before we start our second day. So we have 2 stages. The first stage is the stage you're now visiting. It's Alice, and we have a second stage, Stage Bob, which will start in about 10 minutes. Moreover, we do have a partner workshop from our partner Fraunhofer, which will start at 9:30 and is from 9:30 to 10:30 on real quantum computing insights. And we have a very special opportunity for you to join our unique virtual world during our lunch break, so stay tuned, this is really a unique opportunity. This would not have been possible without the generous support of our partners, which are Atos, Fraunhofer, and Fujitsu, so a great thank you to our partners. And if you are interested in what our partners do, if you want to exchange ideas and if you want to discuss some current topics, please feel free to join the partner area, which is open throughout the second day. But all of this also wouldn't be possible without you, our audience. So despite the COVID crisis, we really encourage you to use this format for networking, for exchanging ideas, and for getting to know other participants. So for that, we have some unique networking opportunities. First of all, we have our own live chat. So you'll see a designated window on the right side of your screen where you have the chance to ask questions to our speakers, to our panelists, but also use this chat to really interact with the audience and to share your insights and your ideas. We also have the unique opportunity to meet some of our speakers after their talks. So there'll be a speaker's corner where our speakers will be for around 15 minutes after their talks, where you can ask follow-up questions and engage in discussions. That's not the case for all our slots, so if you have the opportunity to meet the speaker, I'll let you know prior to starting their slot. Again, please use these opportunities to network widely, and if you want to tweet or write about this conference, feel free to use our hashtag QuantumSummit21. And having said that, it's a great honor for me to welcome our first speaker on our second day. He's from our partner IQM, talking about IQM's fast lane to quantum advantage. IQM is the European leader in superconducting quantum computers. They're headquartered in Finland, but they also have a subsidiary in Munich. And they were recently awarded 12.4 million euros by the federal government, by the German Ministry of Education and Research, to commercialize application-specific quantum processors. With us today is their CEO and co-founder, Jan Goetz, a German-born who now lives the spirit of European collaboration, having founded his company in Finland. And it's a pleasure for me to welcome you, Jan, on stage today for our first talk. The stage is yours.
Thank you for this very kind introduction. It's a great pleasure to be here today and present IQM and what we are doing, and also what our plans are for quantum computing to make it useful for the whole of society. So a fast lane to quantum advantage is the topic of this talk, and I will try to introduce you the company as a general, but then also our strategy, how we think we can create a shortcut to quantum advantage, which is defined as the moment in time where a quantum computer really delivers business value to the customer. So this is the grand goal, which I think most of the community has at the moment in common, is build a machine that can create this advantage for a customer. What you see here on the right-hand side is a rendering of one of our quantum computers. So you see that these systems are still quite large in size. So maybe they remind you a little bit on the very early days of classical computing, where also you had a small room filled of machines. So I think that many of these analogies from the old days in classical computing also work for quantum computing. And of course, the whole community is trying to make them smaller, faster, and better. For those of you who are not so familiar with IQM, I just have here a very brief summary. So IQM, as mentioned, is a spin-out from Finnish University Aalto and also the Finnish State Research Center VTT. We are now more than 100 people working from 2 locations in Helsinki, Finland, and then also in Munich. We are building and also then selling quantum computers. Actually, we have one deal sealed in Finland, and now we are also looking for innovation partnerships where we want to co-develop quantum computers for specific applications. And I will talk more about this during this talk. As a startup, we are funded mainly from private capital. We have raised so far more than 70 million euros, but then of course we are also involved in quite a lot of publicly funded R&D projects. And I think our key message here is that we, as a company, are very keen to co-design application-specific quantum computers. And this is the main topic of this talk, how we are addressing this and how we think that this creates a fast lane to quantum advantage. So this is the whole story in a nutshell. But of course, there's a much bigger picture behind this. And this is this whole topic of quantum computing and what is it good for? What can it actually do? And I think the whole field is really motivated by the big promises that quantum computing makes for all major industries. I think there are ideas how possible applications could be disrupted or improved by quantum computing. And actually quite many of them have the potential to turn the world into a better place. And this is really what motivates us, what kind of wakes up in the morning and makes us work so hard, is building a machine that can create a better world for all of us. And I think there are many ideas out there, and you see some examples here listed on this slide where we think that quantum computing can really help in this vision. And this is, for us, it's very important to use the technology in the right way, and in this way make sure that the whole society benefits from it. So what we do is we build quantum computers. So we are, in the sense, a hardware company, and we are using the superconducting technology. So what you see here on the right-hand side is one of our flip chips. So you see actually 2 chips flipped on top of each other, where the qubits are hidden below this top chip, which is labeled IQM. This superconducting technology is, of course, widely used also by many other players in the field. But as you probably know, is that there are still also other technology platforms out there which are also promising for quantum computing. And what we have been doing in the past 1 or 2 years or so is really thinking very hard about, okay, how can we create this fast lane to quantum advantage? How can we build solutions that allow us to create value faster than with the traditional approach, which is out there. And this is the main theme of today. And we actually think that right now is the right moment in time to do it, because I guess many of you are familiar with the results from the Google team, which were really groundbreaking results on quantum supremacy, which they achieved with, in a sense, only 53 qubits for a random sampling problem. So we see that actually with relatively small amount of qubit numbers, you can already do experiments which would require enormous classical computing power to simulate. So the challenging task that we all have now is to turn this kind of randomness into usefulness. And this is exactly what we have been thinking about. How can we use the qubits? How can we use the chips in a way to create value? And what we came up with is this co-design approach, so that we already see value from these early quantum computers. Some people call them NISQ, noisy intermediate scale quantum computers. And this is what we have been preparing the company for. So we have gathered the right team for it, but also we have been working a lot on the technology and the market understanding, and created a go-to-market strategy on how to use these very application-specific systems for creating quantum advantage. So this has led us to build a whole company strategy around this, which you see here in 3 phases. Where the time is in a sense flowing from left to right. So we are today here on the left-hand side in this foundation phase, where the systems that we build, they are not yet powerful enough to deliver this quantum advantage. But actually, we still think that there is a lot of value in these systems. And this value comes from the fact that they can be used for education and research. And this is what is actually very important nowadays, because there's a global shortage for talent, for example, and there are still many scientific problems which are unanswered. And these two tasks, education and research, these are typically covered by governmental funded organizations. So here our approach in this early foundational phase is actually to build these IQM research systems and sell them then to research centers or university, which use them for this task. And at the same time, we are, of course, developing the technology further. And at some point, the processors will be powerful enough to bring us into this advantage phase. So this is when we then, for the first time, create the quantum advantage for the customers. And we think that this will be in a special purpose system for a selected application. And then application by application, we kind of tap into the market. So to give you an example, it could be that maybe the first low-hanging fruit could be in quantum finance, a problem there. And we provide here a solution to customers, some financial organizations. And then maybe a second problem would be in chemistry, and we would develop a processor which is streamlined for this. So we really have different systems then tackling these different problems. And at the same time, we're developing the technology further and having this grand goal in mind to create an error-corrected system that can provide full quantum advantage for everyone, and then really also try to reduce the kind of entry barriers in terms of costs, computing costs, and these things. And all of this we are doing with our mission to build world-leading quantum computers for the well-being of humankind. And we think with this strategy, we actually find a very nice way to do this now with these IQM research machines, but then also in the future. So how do we actually doing this? What is the concept behind our fast lane or shortcut? So what you see here is a very simplified sketch on the way to quantum advantage, where you see this bluish triangle on the right, where in a sense you have qubit numbers and then also the years, because usually you can translate the number of qubits directly into the years it will take to build such systems if you just follow the R&D roadmaps. And very recently, for example, Google has published their new roadmap based on an error correction strategy, where they say, okay, they aim for a commercial grade quantum computer by 2029. And for us, especially being a startup, of course, we have to try to get into the market earlier, because for us, it's also very important to create early revenue to have the necessary traction that we need to kind of bring the company forward. And this is why we think very hard on how to create this quantum advantage with less qubits, which then also means less years until you are there. And the solution is, okay, we have to use the qubits in a more efficient way than in this error-corrected way. And the way we do it, I mentioned it already a couple of times, is this co-design concept, where actually we really start thinking top-down from the application and think, okay, how is it possible to create an optimal mapping for a certain application on the algorithm, and then also go the subsequent next step, which is actually very important, and how to map these algorithms on the processors, because this is where usually you create a lot of qubit overhead on the hardware side. So finding this optimal mapping, playing certain tricks between the algorithms and the processors, this is really at the heart of the innovation that we are doing in IQM. And what it means is also, because we're doing this for certain applications, is that we are building application-specific circuits, so ASICs for quantum computers. So we call them sometimes QASICs. And the idea is that, okay, with this, we really create a lot of hardware efficiency. And this means we need less qubits and hopefully also fewer gates in the algorithms to reach quantum advantage. And all of this by using the optimal mapping between software and hardware. So this is really the kind of thinking behind this, that we are not optimizing isolated, maybe certain algorithms and then isolated certain processors, but we really think of it in a very holistic way. And the tools that we are using are also kind of covering the full stack, starting at the very high level on the algorithms that we are using. So we are using here a concept which is called digital analog, where we are mixing the best of two worlds. So the standard digital quantum computing, which is based on single and 2 qubit gates, but then we bring in certain analog blocks, for example, multi-qubit gates, where we turn on the interaction between many qubits on the chip at the same time. This is the algorithmic approach, but then we actually start translating it as we go lower and lower in the stack. And the next level could be that we work on the chip architecture. So the way we actually arrange the qubits on the chip. So instead of using the well-known rectangular lattice that works very well for error correction, we could break the symmetry and, for example, go to hexagonal lattices or triangular, or even have more exotic chip architectures. And then if we go one block or one level lower, we come to the individual elements on the chip, so the qubits, but also there actually we are working on novel on-chip building blocks. So this could be novel types of qubits. So actually we are currently working on a new qubit type, which goes the standard transmon type of qubit that most of the people are using. But we're also looking into multi-level systems or using resonators on the chip to take part of the algorithm, where actually the algorithm can be mapped very efficiently into such blocks. And then also between the blocks, actually, we think that we can still create advantage by streamlining the chip design. So kind of adjusting, for example, the coupling between different elements so that they more natively fit to the parameters that we need in the algorithms. And here's an example on how this could look like. So I've taken this algorithm here from this archive paper, which is about option pricing, one of the ideas we have. And then you see the different steps that have to be executed throughout the algorithm. And usually in the beginning, you have to do initialization. And we have very unique technology actually to do this by using certain on-chip elements. Here they are called QCR to accelerate the reset, but also make it more accurate. And then as we go through the algorithm, actually for all of these blocks, we have developed novel hardware ideas on how to speed up the operations and to make them more accurate. And actually, the nice thing about this is that there are also very strong synergies with the main requirements for error correction. So it's not so that with the strategy, we are kind of developing something completely parallel to the error correction approach. We are just saying, okay, for error correction, you need so many qubits that this is further down the road, but actually making the initialization faster or the gates or the readout faster is also something that is strongly required for error correction code. So in this sense, we are creating here many, many synergies. And we are doing all of this really with top infrastructure that we have on the hardware side, mainly in Finland. So we have access there to a superconducting fab line. We have our own setups operating at the moment for cryogenic setups, but we are expanding this as we speak in both locations, Espoo and Munich. And then we are really bringing this into the supercomputing facility as well. This is something that is very important for us also in the strategy to bringing these qubits, these quantum computers into the supercomputing centers. So as most of these things, we don't want to do this alone, but in a partnership approach. So this kind of co-design, actually, we are currently looking for industry partners to do this process for certain applications with us. And just to give you a feeling, the applications that we are currently looking into are manifold, but they are the usual suspects. So for example, in chemistry, we are looking into how to simulate electronic structures of molecules. Then also we are looking on numerical solvers for differential equations. This could be applied in finance or also in battery development. Or then also on the quantum optimization side. So we are at the moment exploring a few selected applications, but also if there are teams out there who think that, okay, with this concept, actually, we might have ideas on how to optimize certain other applications, we are really happy to talk. I already mentioned that one goal of us, of IQM, is really bringing the quantum computers into the high performance computing interfaces. And this is something that we are really actively developing. So in this sense, you have to see the quantum computer more as a quantum accelerator, like you have certain examples also in AI, where you can use GPUs, for example, to accelerate. And this is a similar strategy here. And we have actually already now certain activities in 2 HPC centers, one in Munich, the LRZ, and then one in Finland, CSC. And also we are strongly partnering here with Atos. We hope that we can support Atos by their goal to use quantum accelerators by 2023. On the way there, I mentioned this already, we have already secured the first customer case. This is not yet a quantum accelerator, but it's the first step of bringing quantum computers on premise. And we then hope, as I mentioned, to go the next step together with our partners and really bringing the quantum computers into the supercomputing environments. So there's a lot going on. This is just a snapshot on kind of the main highlights. I don't want to go into all the details, but the company is still relatively young, not yet 2 years old, and we are really moving fast. These first points that you see here are the main achievements that we had with our first funding round. And then actually we closed a second funding round. And since then, again, we have been moving very fast. We have now our first 5 qubit processor running, actually with very nice specs already. And we hope to also be able to publish some first scientific results based on this device soon. And of course, it's kind of the main or most important part is the people who are doing all of this, doing the main work and all the important steps. And in the 2 years, we have been growing really fast. A team of more than 100 employees, really diverse, more than 26 nationalities now. And if you look at the distribution, we are still heavily technology focused. So actually 77% of our people are working on the R&D. And then of course, we have the necessary support functions as well. So in this sense, we are really a scientific organization. We have more than 50 PhDs in the company. We are also actively educating. We at the moment, we are having 10 internal PhD candidates in IQM, which are doing a PhD. And we have been able to get people really from the best places in the world coming back to Europe to work with us on this very important problems. So if you want to work in such an environment with very ambitious goals, but based on trust and in a collaborative manner, we are hiring, and please check out our open positions here. And just to finish up, of course, also a great thank you goes to the whole founding team, which has been doing most of the early work together and creating the plans. And I also bring up these slides to show that actually the developments that we are talking about here, in a sense, they have been started already in the 60s. So this is when the low temperature lab started in Helsinki. And since then, there's systematic R&D going on in this field. And I think that's very important to understand that also if we are now talking, for example, about the situation in Germany, that we really need to build up this kind of infrastructure, the facility, all of this, if we want to make such cases happening and if we really want to build such complex technology together. And then I think if we go this way in a kind of team spirit and a collaborative approach, everyone working in the same direction, I'm very confident that we actually can create solutions out of Europe, which can then also be competitive on a global scale on such an exciting field as quantum computing. So with this, I'm at the end of my presentation. So thank you all for your attention. Again, we are hiring, check out our webpage. And I'm also looking forward to a panel discussion later today, where hopefully we can discuss many of these topics that are raised here. So thanks a lot, everyone.
Thanks a lot, Jan. This was really a great introductory speech, and I especially like the quote you had at the beginning that quantum computing has the potential to turn the world into a better place, because I guess this is also going beyond the quantum computing community, which is really why we're making this conference today. So there was one question from the audience, if you quickly mind. It was on slide 7. You were talking about the option pricing approach. So someone was asking in which step of your roadmap you're expecting to supply it in practice. So maybe you have 1 or 2 sentences about that.
Yes, so this option pricing algorithm is one application that we are looking into. If you check this paper carefully, you see, for example, that it still requires error correction, so many qubits. But actually what we are trying here, and this is this kind of partnership slide, is for example, we would try to find a bank who's willing to work on this topic with us and go kind of a very early adopter and go these steps then together. And we think that this co-design process in the middle here, it can easily maybe take 2 or 3 years or so until we really have a blueprint for a quantum advantage machine.
Great, thank you very much. And thanks for having the time to spend it with us. All of best luck for your future endeavors, and see you soon.